All right, let's jump right in. We're going to talk about a really interesting shift that's happening in artificial intelligence. You see, computers are getting good at not just spitting out answers, but actually reasoning about them, in a way that looks a lot like how we humans think. It's like we're watching them go from being simple calculators to, well, actual creative partners. So, to really get what's happening here, you first have to see the huge difference between these two things. On one side, you've got machine calculation. This is what computers do best, right? They are incredibly fast, super precise, and it's all about one thing: soundness. Getting the right answer. End of story. But then you have human reasoning, and that can be messy. It's creative, it's all about context. For a person doing math, it's not enough to just find a proof that works. You want one that's elegant, that gives you some insight, one that you can actually understand. And this has been the big roadblock for decades. I love this quote because it gets right to the heart of it. AIs can prove some seriously complex stuff, but most mathematicians just don't use them. And why is that? It's because the correct answer isn't all that helpful if you have no idea how the AI got there. For an AI to be a real partner, it can't just be a black box. It has to explain itself, show its work, in a way that we can follow along and even argue with. So, the big question is, how in the world do you teach a machine to reason like a human? Well, one of the most promising ideas is to just flip the whole problem on its head. What if a proof wasn't a straight line from point A to point B? What if it was more like a structured, formal debate? And that brings us to this really cool field called computational argumentation. Basically, it's a way to program logic where ideas don't just exist, they have to compete. The system will build up arguments for something, sure, but it also goes out and actively looks for counterarguments. It creates this whole dynamic web of ideas that honestly looks a lot more like a real human discussion than just a simple calculation. And what's great is that this whole complex-sounding system is built out of just a few really simple parts. It all kicks off with one single argument. That's the first claim you put on the table. Something like, okay, this theorem is true, and here's my proof. Of course, an idea rarely just sits there unchallenged, right? So the next piece of the puzzle is the attack. This is where another argument pops up to question the first one. Its job is to look for any weakness it can find, a logical flaw, a hidden assumption, anything. But an attack isn't the end of the road. A third argument can come in and defend that original claim. It might say something like, nope, your counterexample doesn't apply here, and this is why. And it's this back and forth, this dance of attack and defense, that decides if the first argument really stands up to scrutiny. Okay, so you've got these concepts of attack and defense. How do you formalize that? Well, researchers have basically turned it all into a structured game that machines can play to figure out if a claim is actually valid. They call this game a dialectical proof. It's pretty straightforward. You've got two players, the proponent, who is championing that first argument, and the opponent, whose entire job is to poke holes in it. They just go back and forth making their moves, and an argument is only considered proven if the proponent has a winning strategy, if they can defend against every single possible attack the opponent throws at them. But that's the million-dollar question, isn't it? What actually counts as a win? This isn't just some casual debate. It's a computational process. There are very strict rules about what is and isn't a valid move. And getting those rules, what they call the semantics of the game, just right is a massive part of the research. Now, this whole argument game sounds pretty great in theory, but trying to actually build it and run it in the real world, well, that's where you hit some pretty big practical problems. The thing is, real systems have limits. The fancy term is resource-bounded agents, but it just means an AI doesn't have forever. It has a limited amount of time and memory to figure things out, and that leads to this huge problem of computational complexity. The number of possible arguments can just explode, making it impossible to check everything. And on top of all that, you have to make sure the game's rules are actually logical and don't lead to crazy conclusions. At the end of the day, we're building AI agents that have to think with the same kinds of limits we do. They can't know everything all at once. They have to make smart choices about which arguments are worth exploring, all within a tight budget of time and power. It's a huge challenge for sure, but it's exactly this limitation that might make them reason a little more like us. But look, even with all these challenges, this whole approach is paving the way for a seriously exciting future in mathematics. We're starting to move away from thinking of a machine as just a proof checker and more towards the idea of a machine as a creative, collaborative partner. One of the biggest goals here is to simulate something called Lakatos-style mathematics. The idea from the philosopher Imre Lakatos is that math isn't some clean, perfect process. It's messy. It's human. It's a cycle of proofs, then counterexamples that break the proofs, then refining your ideas. And that messy, human process is exactly what this computational argumentation stuff is perfect for modeling.
So how do you make this happen? Well, researchers are going right to the source. They are training these AI models on thousands of real conversations from online forums like MathOverflow. And this is the key part. The AI isn't just learning logical steps, it's learning the human art of explaining things, of teaching, and even of persuasion, just by watching how the best mathematicians on the planet actually talk to each other.
And that kind of leaves us with this one last big idea to chew on. We are getting really close to creating machines that don't just find an answer and hand it to you. They'll be able to have a dialogue, to understand why you're skeptical, and to build a case that's not just logically perfect, but actually compelling. So what does the future of knowledge even look like when our partners in discovery aren't just calculators, but conversationalists?